Have you ever noticed that when you take bread and you heat it up in the microwave, it heats up a lot faster than a glass of water? There's a couple of reasons for that, but it really doesn't have to do with the microwave. You might think, well, the microwave's just better at heating the bread than the water. That's really not the case, because as long as the microwave is drawing a certain amount of power, it's putting all that power into the cavity. All the energy flows into that cavity, and it's going to go somewhere. Now, it's actually true that microwaves are not 100% efficient. A lot of people think they are, but they're not. There's actually light essentially being shown into the cavity that you can't see. It's infrared light, and if that light gets absorbed by the sidewalls, well, that's electricity you paid for that's not going into heating up your food. But on the other hand, it's a lot more efficient than a typical oven, because in a typical oven you have to heat all of the air in the oven as well. So microwaves can be more efficient. They're just not as efficient as you might think. But in any case, the microwave will draw the same amount of power and try to put the same amount of energy into both substances. And let's just assume for the sake of argument that it succeeds. Okay? There are a couple of reasons why one will heat up, if you will, faster than the other. Its temperature changes faster than the other. One is the mass, obviously, right? If you take a slice of bread and you put it on a scale, take a glass of water, subtract off the mass of the glass itself, obviously. But most pieces of bread have a lot less mass than a volume of water. That's true. So the mass makes a difference. The less mass there is, the quicker it's going to heat up. But there's more to it than that. You see, there's this thing called heat capacity. And heat capacity is the idea that how much energy do you have to add in order to change the temperature. So if I add 10 kilojoules, if I put 10 kilojoules of heat in, so basically I'm changing the bread's internal energy by 10 kilojoules, the temperature will change more drastically than if I take that same 10 kilojoules and put it into a glass of water. Because, even if I control for the mass being the same, it's because the water has a higher tolerance, if you will, for heat or for energy. Now, we don't really like to deal with heat capacities most of the time. What we prefer to do is deal with specific heat. The only real difference is that instead of taking the total amount of energy put into the substance over the total change in temperature, what we do is take the amount of energy put in per unit mass, per kilogram or per pound. We call that lowercase c the the specific heat capacity, or specific heat. And you can think of this as kind of like, I don't drink. You could probably drink me under the table if you're a typical college student, If we went out and I drank something, my tolerance would be very low, right? My change in behavior, kind of like the change in temperature, would be much, much larger for the same amount of alcohol that your change in behavior would likely be, Just because, honestly, I've tried many different things and I can't get past the smell of beer. I don't like it if I can taste the alcohol because I don't like the flavor. And I have no desire to get used to it so I can enjoy it. Same thing with coffee. I don't drink coffee just because I don't like the taste. I finally found that I liked wine coolers. Then I found that I like the juice better without the liquor in it at all. The only thing I've ever found that I kind of liked was Mogan David wine when it's chilled and just open. Then it's usually pretty good, but within a few minutes or seconds it just tastes bad to me. Anyway, so you can think of heat capacity as like a tolerance for energy. It's how much the temperature changes. Or you can think of it as like a container, where something that has a small heat capacity has a small diameter. So putting the same volume, if you want to think about it that way, of energy in will change the temperature more drastically than a wider container, something that has a higher heat capacity or a higher energy tolerance. Now, there are some complications. When we're dealing with solids and liquids, it's not so difficult, but gases are a little bit different, because if you take a gas that's in a constant volume and you add energy to it, say you want to add enough energy so that the temperature changes by 1 degree Celsius. We've got 1 kilogram of helium in a constant volume container, and it's at some temperature. We want to increase that temperature by 1 degree Celsius. Turns out you have to add 3.12 kilojoules to that container in order to change that helium's temperature by 1 degree. But if the helium is in a container that allows it to maintain constant pressure, then you have to add 5.19 kilojoules instead. You may look at this and start scratching your head saying, well, why? Why would there be a difference? After all, you're adding energy, you're getting the same temperature change. Why would the heat capacity, the tolerance for energy, depend upon whether this is a process that occurs at constant volume or at constant pressure? Well, if you think about what's going on, when the piston expands, it's doing boundary work, right? And so because of that boundary work, that's energy that, it's kind of like you deposited $5.19, but the mafia took some out of it, right? The mafia took out the difference between the $5.19 and the $3.12 that your account actually increased, because that 3.12 kilojoules is still in the helium. It's just that the extra energy went out as boundary work. So we define the heat capacity at constant volume as the change in, or the specific heat, as the change in specific energy divided by the change in temperature. And then the heat capacity at constant pressure is the change in internal energy plus the boundary work divided by the change in temperature. And really it's a change in enthalpy per change in temperature, but because this is a process that occurs at constant pressure, it will turn out that delta H, the enthalpy, will be the sum of the change in internal energy and the boundary work. Now that wasn't really fair, because helium's heat capacity, well, it was probably okay, because really helium is one of the noble gases, so its heat capacity really doesn't vary hardly at all with temperature. Of course, on the scale we've got here, you couldn't see if it did anyway. But other substances do vary quite a lot. Their heat capacity varies with temperature. Now, if you look at the x-axis and the temperature range we're talking about here, this is a pretty wide range. I mean, 0 to 3,000 Kelvin, no human can survive that change in temperature no matter the starting or ending point, right? You're going to be a crispy critter at the end of that process. So this is a decent change in temperature, at least on a human being scale, and the scale at which we often do things. I mean, yeah, the engine under the hood is hot, it'll burn you, but still only about 190 degrees or so. You know, the exhaust gases coming out are hotter than that, but still, that's not, 2,000 Kelvin or something. So the interesting thing is that most of these in fact, all that I've shown here, their heat capacity increase with temperature. So they have, you can think of it as a higher tolerance. And as I said before, I don't drink. I don't know that this is true, but I imagine that as you drink more, you probably get a higher tolerance for the liquid, or for the liquor, and so you tend to drink too much because you don't realize that you're hitting your limit. I don't know if that's true. Maybe it works the other way. Someone can tell me later if they want. But that's the way this works. As the temperature of the substance goes up, the amount of energy required to get the next change in temperature is bigger. Okay. To better understand heat capacity, let's start with ideal gases, because they're simpler. As a matter of fact, several in the past have performed this experiment. It's usually credited to Joule, but there were others that performed this experiment as well. And what he wanted to find out was, if he allowed air at high pressure to expand into an evacuated cylinder, how much energy does that give up? Because everybody understood that if you have a container and you put pressurized air in it, there's some energy there available for use. So he reasoned that, if you allowed this to expand to a bigger container so the pressure dropped, well, you can't do much work with that, right? Not as much as you could with a high pressure air. So apparently energy's somehow been lost. So he came up with this experiment where he put these cylinders that are connected by a valve into a water bath. And his reasoning was, well, if I open the valve and air rushes over to the other side, I'll have air at a lower pressure. Obviously the system has lost some energy, so I should be able to measure that as an increase in the water's temperature. So he performed the experiment, opened the valve, and it turned out that the thermometer did not change temperature at all. And so what he figured out from this is that the internal energy of the air depends only on its temperature. Because think about it, the pressure of the air certainly dropped, right? Yet the temperature remained the same. And so the amount of energy in the water must not have changed. So for at least ideal gases, the internal energy is equal to it's a function of temperature only. So if we write the ideal gas law in our form of PV equals RT, and we remember that the definition of enthalpy is U plus PV, then we could replace PV with RT. And what you'd find is that for an ideal gas, the enthalpy, which depends on the internal energy, and RT, well, internal energy depends only on temperature. RT, well, R is a gas constant, it doesn't change. T is just temperature. So enthalpy of a gas, or of an ideal gas, is also only dependent upon the temperature of that gas. And this is actually really handy, because what it means is that we can have tables of ideal gas properties in the back of our book. In fact, you should go to the back of the book now. This is something you didn't have in the past course. There are tables of ideal gas enthalpies and internal energies and properties of air. I believe it's A17, but it may be A17, A19, I don't know. Go back and look. You should mark those pages. I'll refresh your memory on those when we actually use them. We won't use them quite yet. But when we get around to using them, I'll make sure you know where they are. But for now, you know, if you can, grab a tab and go tab those pages, because they're very useful. Now, the way that heat capacity is really defined is in differential form. So a differential change in internal energy equals the constant volume heat capacity times the differential change in temperature, and a differential change in enthalpy is equal to the constant pressure heat capacity times the differential change in temperature, where those temperatures that are in parentheses just means that the heat capacities are a function of temperature, now that we realize that's true. Now, I'd like you to write this down, because one of the problems students get into is they think that if they have a constant pressure process, they can't consider CV. CV can't be used in any way because this is not a constant volume process. That's not actually the case. I want to build a bridge in your mind where you correlate CV with DU and CP with DH. So please do me a favor, grab a pencil and a piece of paper. I don't usually ask you to do this. Write these two equations down that are in the boxes, and I will ask you to do this many times over in the course so we can build that bridge, because it's important that you realize you can use constant pressure heat capacity in a constant volume system and vice versa. You just have to know what you're doing with them. So taking these two equations a little bit farther, we realize that they are differential equations. Maybe it would be good if we integrate them, because after all, enthalpy and internal energy are properties of the system itself, and so we could talk about changes in those properties from one state to another. So if we integrate du CV dt, the left-hand side obviously would just be the change in internal energy, and the right-hand side would be the integral of everything on the right-hand side. Same thing with enthalpy. Delta H, H2 minus H1, would be the integral of Cp dt. Now, what are we really doing? Well, you remember that heat capacity varies with temperature. What we're really doing is adding up the area under this diagram, where we have heat capacity on the y-axis and temperature on the x-axis. So really what we're trying to do is find this area. That's what that integral means that we had on the last slide. And since my vertical axis is the constant pressure heat capacity, I've appropriately written the change in enthalpy here. If my vertical axis was CV, the constant volume heat capacity, then the change would be a change in internal energy that we'd be calculating. So this is the actual area that we would like to calculate. Now remember that the distance, the scale on our x-axis is very, very large. Most processes will not have that large a change in temperature. So the heat capacity wouldn't change much across that temperature range, since the temperature range is small, and we could take some average heat capacity and, rather than having to integrate, still get a decent estimate for the enthalpy change by just using the average heat capacity times the temperature difference. And so you can see how this would work, right? Where you've got the average heat capacity on the vertical axis and then the change in temperature on the x-axis, and then Cp times that delta T would simply be the area that we see up here, just the area of a rectangle, because obviously you can cut off the one triangle that's above the average heat capacity and fit it below the heat capacity in the area that's missing, and this is just the area of a rectangle. So in that case, it's easy to calculate the change in enthalpy without integration and still get, reasonably good results. The limitation on this equation is that the difference between T1 and T2 can't be very large. Well, what do we mean by that? Well, basically a couple hundred Kelvin would be fine in just about every situation. Sometimes 1,000 Kelvin might be okay. But what you really need to know is how much the heat capacity changes as the system moves from one state to the other. Now, if we can approximate the heat capacities as constant, then, as I said, it's easier to perform the integration, because the heat capacity just comes out of the integral, and we just have the heat capacity either at constant pressure delta T equals delta H, or CV delta T equals delta U, the change in internal energy. Now, one thing we can do, considering the definition of enthalpy, we could write it in differential form, right? So we could take the differential of the equation. And remember from calculus, when you have a product and you try to take differentials, you have to hold one constant, differentiate the second, differentiate the first, hold the second constant. Well, the reason that term does not appear in this equation is because there is no change in the gas constant R. dr would be exactly 0. So the term dr times t goes away. But other than that, we're still following the rules of calculus. It's just one of the items is a constant. Now we can change dH for Cp dt, and we can change du for Cv dt. If we do that, what you'll notice is that we have this differential variable dt throughout the equation that could be canceled, and we end up with a relationship between the constant volume heat capacity and the constant pressure heat capacity, along with the gas constant R. So you should go to the back of your book where the tables are located, and you should check to make sure that this always works, because you'll find a table, it's the first page or so in the appendix, where Cp, Cv, and R are listed, and you can simply add the Cv and R and see that you get Cp. Now while we're here, you'll notice that there's another column back there that is the ratio of Cp over Cv, and it's defined as K, the ratio of heat capacities. We're not going to use that right now, but we will use it later, so I went ahead and pointed it out where it is located in your text.